We're now going to take a look at another operation that involves vectors, but we can't really describe it as an arithmetic operation. It's not like um, addition or scalar multiplication. It's a different operation, and it's called a dot product. And it has other names as well, which I'll give in a second. But basically, when you think of the operations that we've done before, like when we do vector addition, we take two vectors, whether they're in R2 or R3, and we add them together and we get a third vector. With scalar multiplication, you take a scalar and you take a vector, you multiply them, and you get another vector. Well, the dot product is different in the sense that it's an operation that will require two vectors, but when we perform this operation, we're not going to get a vector, we're going to get something different. So let's go ahead and define what it is. And what we will do is we will give an algebraic definition of the dot product, and then we will derive a very important geometric equation, right? So the dot product has two ways that it can be calculated algebraically and geometrically. So really important stuff. So let's go ahead and define the dot product, and I'll do it for both R2 and R3. So if u is the vector u1 comma u2, and v is the vector v1 v2, right? Then the dot product, so the dot product of u and v, right? And it's denoted, this is how it's denoted. It's u with a dot in the middle. Kind of, like it looks like the dot that you would use when you're multiplying two numbers or two scalars. But now we definitely know that these are two vectors, and this is how it's defined. You take the first component of u and multiply the first component of v, so you do u1 v1. You take the second component of u and multiply the second component of v, and then you add these two products together. And what we're going to end up with is a scalar. So this is actually going to be a real number, right? Which is important. So when we compute the dot product of two vectors, we don't get a third vector. What we end up getting is a scalar, right? And similarly, right, if let's say we have three-dimensional vectors, if we have a vector u1, u2, u3, so these are this is the component form of u, and let's write down the component form of v, so that is v1, v2, v3. Then the dot product of these two vectors, you might guess, we're essentially going to do the same operations, but now include the third component. So it is going to be u1 times v1 plus u2 times v2 plus u3 times v3. And again, this answer is going to be a scalar, not a vector. All right? So let's just do a couple examples illustrating this. Again, the actual operations, the computations, are very simple, but we have to now start getting used to the different operations that we're doing with vectors. So let's do our first one. So let's choose u to be, I don't know, 3, -6, and let's say v is the vector, let's say -4, 2. So then the dot product of these two, so u times v, that's equal to, so it's going to be 3 times -4 plus negative 6 times 2. So this is negative 12 plus negative 12, which is negative 24, right? Now you can get any number, right? You could get any number as an answer of a dot product question, right? Let's look at a 3D case. So let's say, and just for fun, let's express these vectors in terms of the standard unit vectors. So I minus 3j plus 6k, and then let's say v is negative 3i and then minus 5k, right? So let's write down the dot product of these two vectors. So u dot v. So the first component of u is 1. The first component of v is negative 3. So that's going to be my essentially u1 times v1. And then plus the second component of u is negative 3. Now, when you look at the way this, we know it's a three-dimensional vector, right? Because we can see the k, but there is no j. And what that means is the coefficient of j is 0, meaning the second component in the vector v is 0. So there's actually a 0 there, right? So look out for stuff like that. And then plus, what do we have? Third component of u is 6 times, and then the third component of v is negative 5. So we end up having negative 3 plus 0 plus negative 30 for negative 33. That's our dot product of these two vectors, right? So once the vector is given to you in component form, right, this algebraic definition of the dot product is really easy to compute. Now there are other names that are often used to refer to the dot product. So dot product, obviously that's our go-to name, but that it's also sometimes referred to as a scalar product, because the result of performing this kind of product is a scalar, so it's often called a scalar product. And there's a fancier, more general term, again, and this is for more advanced work with vectors and in linear algebra, that refers to something known as an inner product. So it could also be referred to as an inner product. And in our context, they're all saying the same things, right? So we have this new algebraic operation for vectors, and as soon as you learn about an algebraic operation, then you start to think, well, what are some of the properties of this? So let's state. And this is really a theorem, and it has several parts to it. I'm not going to prove all parts. I'm just going to show you the proof of one of the parts. And so here's our theorem. And this theorem, it requires three vectors. So if u, v, and w are vectors in R2 or R3, right? And if k is a scalar, then here are a couple important things. And a lot of these, you often take for granted, but it's nice to at least state them to say, okay, yep, this is a real thing. We can actually do this. And the first one is that your dot product is commutative. In other words, if you take the dot product of, in this order, u dot v, or if you take it in the order v dot u, you're going to end up with the same result, right? So that's good. So this is the commutativity property. There's also a distributive property, which is nice, you know, and this is so this is almost like a vector form of the distributive property that you're used to, and this is what it is. If you have u dot the sum of v and w, you can distribute this dot product over this vector addition. So you can write this as u dot v plus u dot w, right? So you have your distributive property there as well. Just keep in mind now that these are vectors, and what we're performing here is this dot product. There's also the associative property. So let's say you have your scalar, and this is where I need my scalar k. So if I have my scalar times u dot v. Now, this is where you have to be a little bit careful, because this is you're multiplying a scalar, and notice after the way this order of operation is indicated, you would do the dot product first, which will produce a scalar, and then you essentially multiply those two scalars. Well, it turns out that you can sort of group this k in different ways. You can write it as like ku dot v, right? Or you could do u dot and then kv. So this is essentially the associative property that is associated with the dot product. Part D, this is actually a really important result, and this is the one that I will show the proof of because it's not very long, right? And it's good to see it because it is something that we are going to use. But if you take the dot product of a vector and itself, so if you do like v dot v, what you will actually end up getting is the magnitude of the vector squared, which is interesting. So we've talked about the magnitude, and we've done some questions involving the magnitude, and now we're seeing how the magnitude relates to the dot product. And then E, this is a pretty simple one, but it basically says if you take your 0 vector and do the dot product with any other vector, well, you're always going to get 0, right? Right. So this is a property as well. So this is similar to saying like if you take 0 and multiply any number, you will always get 0. This is saying if you take the 0 vector and do the dot product with any other vector, you're again going to get the number 0. And notice over here I have the harpoon on top of this 0 indicating a vector versus this is a scalar. All right, so let's just do the proof of D, right? If you want to impress me and try to prove the other ones, and you could pick either R2, R3. I'm going to do my proof in R3. So let V be the vector, and with your proof, it has to be general, right? It has to work for every possible vector in R3. How do we write that down? Well, we just write down the generic vector in R3, where you can have any number here, any number there, any number there, right? So, I mean, this one is it's really straightforward. So all I'm going to do is I'm going to do the operation here on the left, see what I get. And I'm going to do these operations here on the right, see what I get, and compare them to see if they're the same. If they're the same, then I know they're equal, right? So first let's do our dot product of V with itself. So what that means is, in fact, let me write it down. So it's V1, V2, V3 dot, again with the same vector, V1, V2, V3. So using our algebraic definition, we're going to multiply the corresponding components and add, right? So it's V1 times V1 plus V2 times V2 plus V3 times V3 But v1 times itself, it's v1 squared. v2 times itself is v2 squared. And then v3 times itself, that's v3 squared. And this expression here should look familiar. Think back to when we were computing the magnitude of a vector, where you look at what you ended up doing here is that here are the components of v, and when you take the dot product of v with itself, we end up squaring those components, right? Which is something that we had to do when computing the magnitude. In fact, let's go ahead and do the magnitude now. So the magnitude of v, yeah, and we just write down what that is, right? It's going to be an expression. So it's the square root of v1 squared plus v2 squared plus v3 squared. This implies, so if I now square the magnitude, then I'll get rid of the square root. So it would be the square root of this thing, and then I square the root like that. So the square root goes away, and I'm left with v1 squared plus v2 squared plus v3 squared. And there we go. These two things are the same. So therefore, if you take the dot product of a vector with itself, so v dot v, it's the same as squaring the magnitude of v. So this implies that v dot v is equal to the magnitude of v squared. And that's our QED. All right. The other ones are very, very similar, especially part A. Part A is very straightforward. You can go ahead and try that. But I just wanted to do this one because this is a result that we will use several times over. All right. Now, alternatively, notice another way that this can be written. This is saying that I can, if I took the square root of both sides, right? So I'll just say alternatively. I didn't want to put this in the proof because it wasn't a part of the statement, but alternatively, we could say that the magnitude of v is the square root of v dot v, right? So basically, here is v dot v. If I just put a square root over it, just put a square root over all of these things, and that will be the equivalent to the magnitude of v. So just different ways that it can be represented. Right? So that's some of the algebra that's associated with the dot product. But what about the geometry? What really is this number? What does it tell us? Well, in order to answer that question, we have to look at an alternative formula for the dot product. And in order to come up with this alternative formula, we have to introduce the concept of the angle between two vectors, right? So the angle between u and v, right, is the smallest counterclockwise smallest counterclockwise angle through which one of the vectors can be rotated in order to align with the other vector. So in order to align with the other vector. So again, that sounds like a lot, but it really isn't. So once I draw these two pictures, it'd be very clear. So let's say I have my two vectors, and again, they are going to be concurrent. In other words, they'll have the same initial point, and the angle that we define, the angle between them, and I'm going to call the angle theta now. So the way these are positioned, so we're going to rotate either one of these vectors counterclockwise. And in this case, the smallest counterclockwise angle, I would have to start with V and rotate it this way in order to coincide with U. So this is the theta, right? So that's what it looks that way. What if they are positioned like this? So let's say this is V, and then let's say this is U. Then again, the smallest, so yeah, let me write this. Here is V, here is U. Then the smallest counterclockwise angle, now I would start with V and rotate it, let's see, actually, I would start with U and rotate it this way. So it wouldn't be this angle because that would be, that would not be the smallest, right? So I would start with U and rotate it that way, and then that would be the theta, right? So this is what we define the angle between two vectors to be, and then this definition implies right away that theta has to be between 0 and pi. So it could be like this, right? So the angle between the vector is always between 0 and pi, or 0 and 180 if you like to use degrees. So what do the extremes look like? Well, if the angle between the vectors is 0, then it means that they already are aligned. So they look like this. That would be your U, and let's say that would be your V. So this is where your theta is equal to 0. What would it look like when theta is equal to pi? Well, that means they would have to be completely, they'd have to be acting in completely opposite directions. So you'd have to have like a V there and your U there, and then this would be your theta. Again, going that counterclockwise, right? So this would be when your theta is equal to pi. So and then in other, so when theta is equal to 0, they're pointing in the exact same direction. And when theta is equal to pi, they're pointing in opposite directions. And for theta strictly between um, uh, 0 and pi, then it's somewhere between these two extremes, right? So you might be wondering, what in the world, right? What in the world does this have to do with the dot product? Well, let's see. So I'm going to draw, I'm basically going to take something like this, and this is what I'm going to do. So let's say we have this scenario. We have our U, and we have our V. And now, if you remember when we were doing the geometric way of interpreting the vector arithmetic, we could come up with the idea that this vector, this diagonal vector going from here to here, would be V minus U. So this vector here, right, is the vector v minus u. And then now we can talk about the angle between them, right? And what we have is this triangle, right? So we have this triangle, and what we can actually use is the law of cosines. So by the law of cosines, now the law of cosines, I don't know if it's something you've used quite a bit, but the law of cosines, what it does, it relates these two sides and the angle subtended between them with the length of this opposite side here. And what it basically says, it says that the length of this side squared. Now, the length of that vector is just its magnitude. So I'm going to write this down as the magnitude of v minus u. And the law of cosine says that that squared is equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times the cosine of the angle between them. All right? And there we go. So now this is where we're going to use some of the properties of our dot product. So let's take a look at this expression here. So let's see how we can write this. Now this is the magnitude of this vector squared. Well, part D of our theorem says that we can express the square of the magnitude as a dot product. So in other words, this would be the dot product of v minus u with itself. Right? But then we can use our distributive property. So this is what I'm going to do. I'm going to take, so this would be v, let me kind of write it out in stages. So this would be v minus u dot v, and then minus, again, the quantity v minus u dot u. So basically, essentially what I'm doing is foiling this out, but everywhere, you know, there's a times, it's really a dot product. So FOIL again, this gives me v dot v minus, and then what do I have here? U dot v, and then minus v dot u, and then here I have plus u dot u. But now let's use some more of those properties. V dot v is the magnitude of v squared. Now, from the commutativity property, these two are the same. Whether I take u dot v or v dot u, they're equal, and I have two of them, but they're negative. So this will be negative 2 dot v, and then over here, this will be plus the magnitude of u squared, right? So that's the left-hand side of the law of cosine. So let's plug it back in and see what happens. So what I'm going to do is take this and replace this. All right? So therefore, what do we have? So I'm going to write the magnitude of v squared minus 2 u dot v plus the magnitude of u squared, and then write down what I have here. In fact, I get, oh, let me do this. So then this is equal to the magnitude of u squared plus the magnitude of v squared minus our 2u, here we go, minus 2 magnitude of u times the magnitude of v times the cosine of the angle. Well, what happens here? Well, let's look closely. On this side, we have a magnitude of v squared. On this side, we have the same term. So that goes. On this side, we have the magnitude of u squared. On this side, we have the same thing. So these two terms go. So now we're left with something that's, so look here, we have now negative 2u dot v, and then is equal to negative 2 magnitude of u times the magnitude of v times the cosine of the angle. Now dividing both sides by negative 2 gives us a really useful geometric formula for the dot product. So this tells me that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors, right? So this, and let me kind of box this off, this is a big one. This is a really good result. And this is an alternative formula for the dot product, but it is a geometric formula because look at what it's referring to on this side. It's saying your dot product can be expressed in terms of magnitudes and angles, and those are geometric concepts, right? So this is a geometric formula for our dot product. All right, and I think now, so once we have this, it kind of opens up even more properties of the dot product. But I think let's end this video with a really standard calculation where we can use this result, right? In fact, we can use our two formulas. Let me write the two formulas there now that I'm thinking about it. Let me write this down. So remember, these are the two formulas that we now have, and I'll state this one in terms of R3. So this formula now is the algebraic formula for the dot product. All right, and so which one do we use? Well, let's end with an example that allows us to actually find the angle between two vectors. Because if you think of everything here now, we know how to find components, we know how to use this formula, right? So we can compute this. We know how to find magnitudes. The only thing we've not really found yet is the angle between two vectors. So let's do that as our final example. So we're going to find the angle between, and here are the two vectors. Say v is I plus 2j plus 2k, and let's say w is negative 3i plus 6j plus 2k. Right. So there are the two vectors. Let's see if we can compute find the angle between them. So the first thing I'm going to do is use the algebraic formula to find the dot product, right? So let's first find the dot product here of v and w. So v dot w, that's equal to, so that's 1 times negative 3 plus 2 times 6 plus 2 times 2. What do we have there? So negative 3 plus 12 plus 4. So that is, so what do we have there? 6. So that's 13. right? So next up, so now that we have the dot product, let's go ahead and compute the magnitude. So let's figure out the magnitude of V and the magnitude of W. So the magnitude of V, that's equal to, so let's take the components of V, square, add, and take the square root. So that's 1 squared plus 2 squared plus 2 squared, taking your root. So that is the square root of 9. Oh, that works out nicely. So that's 3. And let's compute the magnitude of W. So the magnitude of W, same calculation. Square each component and add, and then take the square root. So this is the square root of negative 3 squared plus 6 squared plus 2 squared. So this is the square root of 9 plus the plus 36, which is 45, plus another 4. So that's 49. Hey, another perfect square. So that is 7. And then, so now that we have the dot product, we have the two magnitudes. The only thing we can use our geometric formula to then figure out theta. So therefore, the dot product, which is 13, is equal to the magnitude of u, or I'm sorry, magnitude of v, which is 3, times the magnitude of w, which is 7, times the cosine of theta, where theta is the angle between these two vectors. So doing a little bit of algebra, so 13 over 21 is the cosine of theta. Therefore, theta, using our arc cosine, so arc cosine of 13 over 21, and so in degrees, this is approximately 51.7534 degrees, right? So so basically we're able to use both formulas, the algebraic and the geometric formulas, right? Using this one to figure out the dot product, and then use this one to figure out the angle, and that this gives us a nice way of computing the angle between two vectors without ever having to sketch them, right? So these are two vectors in R3, and with a few basic calculations, we're able to compute the angle, right? In our next video, we're going to look a little more deeply as to some properties that we can understand about the vectors based on these two formulas for the dot product. So see you then.